So many materials have some crystalline structure, some periodic repeated structure, and this is well analyzed using X-ray on an atomic or molecular level. And so let's assume that we have planes of atoms, like sheets of atoms, and the sheets themselves are spaced by some distance d. We can bombard this with appropriate sized wavelengths and use interference to get information about the spacing between adjacent planes. As it turns out, for materials purposes, the X-ray is a good wavelength just by dint of the typical spacing between planes of atoms. So probably not going to be able to draw this the way I want. It's not terrible. Goodness. Okay, so we have some X-ray source, and we're going to put some detector here. Symbol I use for detectors is usually the human eye. Your eye isn't sensitive to X-ray, so it wouldn't make a very good detector.
The X-ray should be only used in the hospital, right?
It's also used in a lot of physics and chemistry labs, and engineering labs too, actually.
Oh, okay. It's fine though.
Material science engineers, condensed matter physics, a lot of the chemists. So I'm going to pick.
This is a person's eye?
Well, I'm using that as just a symbol for a detector. I had a research advisor who once said that undergrads and grad students were inexpensive enough that they always made good detectors, at least as a first try. So he'd say that grad students were cheaper than actual detectors.
Okay.
This wouldn't be very useful. You can't see X-rays. So, in fact, it would probably just be detrimental. It's not, X-ray exposure is bad for you. So. So don't do that. Even if your graduate research advisor says it's worth a try, it's not. Do you see that these two rays travel the same distance up to here? Yes. Maybe if I don't hold the pen. That these two rays travel the same distance up to here?
Yeah.
Right, and so I could just draw a perpendicular line to that. Mm-hmm. Then this ray traveled this extra little distance, yeah? Mm-hmm. And then upon scattering, this one travels back, so theta from here on, right, those two travel effectively the same distance, right? And so I have a pair of right triangles here. What is this extra travel distance? This is my poor drawing. Oh, wait.
You want that in terms of the distance between layers?
Oh, would it have helped if I had actually named it?
D sine theta.
Yeah. So this is d sine theta, and this is also d sine theta, yeah? And so what's the extra travel distance for ray 2?
2D sine theta.
2d sine theta. And if I want constructive interference, what does that need to equal?
2D? No.
Constructive M lambda.
M lambda. Yay? So this is the so-called Bragg's law. It's the kind of the meat of X-ray diffraction. There's a lot of subtleties beyond this, but as a first pass, this is a good go. After you've had some quantum mechanics in a few weeks, we can come to expect that for some distributions of particles in plane, we may not get every constructive interference that we expected, but that will actually help us pick out which material we're talking about or what crystal structure. So, 30-ish minutes. Okay. Let's make sure that I mention Raleigh's criterion. I never do this, but how about a free 3 points on the exam?
What? What did you say?
Yes, please.
So,
I'll take anything.
so I'm about to talk about Raleigh's criterion.
What?
I don't know if those two prior sentences are at all connected.
What?
What are you going to do?
What's Raleigh's?
I'm about to put it on the board. So, I never, I hate teaching to the test. I think it's unforgivable. But I'm about to put something on the board. I don't know why I would bring up those two things immediately in succession, but draw from it what you will.
Let's draw this.
Oh, good golly. There's a conceptual question on Raleigh's criterion.
Okay. Now we can guess.
Okay. Still lost.
Okay, so we've previously spoken about
That's how I can pass.
diffraction, right? And what we came to say is that for single slit diffraction we had that sine theta dark just went as m times lambda over a, where m is some integer not 0. Yay? And this kind of yielded something like that, yeah? Where this might be white arc 1, white arc 2, white arc minus 1, white arc minus 2. Yay? Okay. So let's talk specifically about what Raleigh's criterion is then. So we've said previously that when you go to the DMV and they give you the eye test, I don't think they actually care that you know it's an age, right? What they want to know is that you can see those two adjacent lines. And so what they're really testing is from what distance can you no longer tell that there are two objects instead of one blurry object. Yeah? So Raleigh's criterion tries to describe this for you. So let's imagine that you've got two sources. I call this one 1, I'm very imaginative, and this one 2. And so Raleigh's criterion is this idea of at what, how close can you get these together where you can still resolve two distinct central peaks. And so the Raleigh's criterion is when the central max of one image falls on the first min of the second image. Both of them are just barely resolved. And so in other words, if this
What?
right central max shows up as the first dark spot of the first image, then you can still see 2. But if you bring these any closer together, it's just going to look like one blurry object. It'll look like, I don't know, something like that instead. That's the Raleigh criterion. Yay? So, for a circular aperture instead of this rectangular slit, so by the way, what does that say about theta minimum for resolution? So for small angle, sine theta is approximately theta. And so theta min for resolution is roughly lambda over A. If you let theta be any smaller than that, you won't be able to resolve. That's for rectangular slits. If you have a circular aperture, instead of a rectangle slit like this, you have a circular aperture. Then theta min is about 1.22 times this instead. Where d is diameter. Questions, comments, concerns?
Where did you get the 1.22 come from?
This is going to just seem like I pulled it out of nowhere because I did. It comes from solid angle, and I'm not gonna. I don't have time to go through that. But just switching from a narrow slit along one dimension to something that has many dimensions, right, or many axes. So, but the derivation is long enough that it's not worth doing it.
Oh, okay.
Wait, theta min, you're talking about the angle between the two sources?
Yep.
I don't know why it would be lambda over A.
Because that's effectively how much you're shifting one of the central peaks from the other. Right? And so since the first minimum shows up at lambda over A, you can't shift the central peak of one of them by less than lambda over A without having it become blurry.
Oh, okay.
Maybe it would have been smarter if I had let one of these be straight on and just let the other one be angled off the side. Maybe that's more visible. It's not what I did. Okay, so if, oh, sorry, is it okay if I move this?
I won't. Okay, it's okay, thank you.
So what is what's the role of a telescope?
Telescope? Which guys can look far away?
Magnify object at extreme distance?
So, telescope has kind of three main functions. The first two are kind of the where I would invest your resources. The third is the one that is easiest to correct after the fact. So, telescope collects light to view dim objects. So that's maybe the most important facet of a telescope. It also helps to resolve, I'll call it resolution. It's resolving between two objects. And the third is magnification. These first two are kind of the key things for a telescope. So when you go out and look at stars at night with your eyes, what color are they?
You mean look at what?
They look white, yeah? Have you ever looked at a NASA image of stars?
No,
No?
no,
apod.nasa.gov.
no.
Like yellow.
Every color of the rainbow. So, why do they appear white?
They have all
It's all
kinds
colors,
of light.
right?
Nah, the individual stars, I mean, if you look at the individual stars, every color of the rainbow. So, why, if you look at a star at night, does it seem...
Is white the only wavelength that makes it through?
Nope.
Wait, that's not even a color though, that doesn't make sense.
Mine looks white.
We talked about this on Monday.
Because of the resolution?
It's the wavelength?
Rods and cones.
Oh, rods and cones.
Why do stars look white?
It's how rods to do something. Oh, rods is not sensitive.
The rods aren't color sensitive, it's true. So why, then the next question is, why don't I use the cones to look at the stars?
I have no idea what you're talking about.
So, okay, two kinds of photoreceptors, rods and cones. We talked about that on Monday. So one allows me to detect the presence of light, one allows me to detect colors. Which one's which?
Colors is a cone.
Colors, cones,
Yeah.
light detection in general, rods.
Yeah.
Why don't I use the cones to detect the colors of stars?
We say we have a small amount compared to the rods.
We do, but what's the which one takes more light to trigger to send a signal to my brain?
Corner.
The cones do, right?
Oh, the cone, yeah.
So what's the problem with trying to determine the color of the star with my eye?
Not enough
Not
light.
enough light. It's
Oh.
too dark. It's too dim. I have to use the rods to see them. Yeah.
Yeah.
So it's not that the stars are all white. It's that my eyes can't collect enough light to use the cones. Yeah.
Yeah.
So then, what part of my eye is, like, how my telescopes are often referred to as light buckets. You could imagine going out in the rain and collecting light or collecting rain. Maybe this is a physics fraternity, what do they call those? Hazing? Pledging?
What's the difference?
I don't know. If you have to collect as much rain as you can, but as a physics major you probably don't get to go outside much, you might be worried about, you know, melting in the rain. You don't want to be out there for more than a few seconds. Should you take a pot or a teacup?
Pot,
Why?
more surface area.
Is either of them, yeah, so neither of them's going to fill, right? So, but the one that has more surface area,
Got more chance to catch the rain.
is going to collect more rain. Yay?
Yes.
What part of my eye is used to collect light? The dark center region, right? So let's assume that it's roughly circular, cross-section. So what's the area? Pi r squared? Pi d squared over 4? Guesstimate about what's the diameter of my pupil. Remember, by the way, I love the eye. I'm sorry, I have all sorts of, as I was walking to my car on Monday, I was thinking of all the little bits of trivia I didn't give you. When you, they've done studies, when you look at something that you like, or a person that you find appealing, the pupil actually widens. In some level, you're trying to let more light in, whether consciously, unconsciously. Like, when I see a Milky Way candy bar, you can't even see like the colored outer region of my eye. At night, your pupil expands, right? Tries to let more light in. Guesstimate. How wide is it?
Is it 8 millimeters?
What's
2
this?
inch, 1 inch,
8 millimeters?
1 inch,
Sure, that's about,
2.5.
that's in the family. So, can I round it to 1 whole centimeter? Because
Sure.
I don't want to do math.
1 centimeter?
It's not. That's a little too big. But that's like cartoon character size pupils. Roughly, what is this? Pi over 4, that's about 3/4. 0.01 squared, 10 to the minus 4. So that's about 7.5 times 10 to the minus 5 square meters. Is that okay? Roughly? So, the reason I'm standing in front of you is because everything I ever got was a hand-me-down. Like, I have 2 older brothers. Right? Everything I ever got was pre-broken, except for a telescope that they apparently had no interest in. It was still pretty much brand new. So, wasn't, a super fancy telescope, but it was, it was mine, and that kind of got me interested in the physical ends of science, but I don't know. I think it was probably a 3-inch diameter telescope. So, I don't know, let's say about, I'm going to overestimate because I don't want to do math. Let's say it's about 10 centimeters diameter. So, my very, very starter telescope, roughly, so also circular cross-section. Area is how much bigger?
100 times.
100 times bigger. So its ability to collect light is about 100 times bigger. Yeah? So it can actually start to provide some ability to gather color information here, right? This is, how is it going to help resolution?
It's not.
Well, what happens to theta min for a circular aperture? How does it scale? Scales as 1.22 lambda over d. So for the same visible wavelengths, if I make the diameter 10 times bigger, what does it do to the size of the angle that I can put two stars before they look like one blurry star? Makes it 10 times smaller, right? I can put them much, much closer and still be able to see them. Telescopes allow us to see finer detail than you can see with your unaided eye. The last thing is magnification. That comes largely at the eyepiece. And the eyepiece on most telescopes you can swap out. You can't do much about the size of the objective lens, how wide the diameter is, after you've purchased it, right? But the eyepieces you can, for most telescopes, you can replace those after the fact. Does it make sense why diffraction becomes less as you increase the effects of diffraction become less as you increase the diameter? Think about this in terms of light is encountering an obstacle. Is the narrower hole or the bigger hole more of an obstacle for the light?
The smaller hole.
The smaller the hole gets, the more of an obstacle it is. My cartoon physics thinks of Tom and Jerry, the cat and mouse. The mouse hole isn't really an obstacle to a mouse. It is an obstacle to a cat, right? So as you increase the diameter, you have less bending of the light as it encounters this obstacle. Does that work for you? Conceptually, why diffraction is lesser for the wider aperture? All right. Then. Then, you know what? Go enjoy 2 extra minutes of sunshine.
Oh, yeah.
As always, you guys are awesome. Have wonderful days. Thank you for stopping by. Don't be strangers. Enjoy your days, but not so much.
Thanks.
Go see you next time.
All have dinner.